attribute. But we also look at the sample proportion. So the sample proportion is very similar to the population proportion, such as if we were looking at the population of individuals that have a full-time job and go to school part-time, then that's the population proportion. But maybe we might want to look at just a sample so that we can be able to estimate a parameter based off of a statistic. So this sample proportion is denoted p hat equals to x over n. Okay, so p hat is just where we have that x is the number of members in the sample with the specific attribute, and n is just the sample size. Now, we'll kind of start off by just doing a really easy example where we have that we're just going to compute a sample proportion. So, a professor surveyed a random sample of 420 statistics students. One of the questions was, will you take another math class? The results show that 252 of the students said yes. What is the sample proportion, p hat, of the students that who say that they will take another math class? So this one's actually pretty easy because we have that the n, which is the sample, is equal to 420 students. The x is the number of individuals that said yes, so that's going to be 252. What this means is that p hat is going to be equal to, that's going to be x over n, which is equal to 252, all divided by 420. So if we do this computation, this is going to give us that 0.6 are the sample proportion of students that will take another math class. So this question was only just asking for just the sample proportion. So whenever you're trying to solve this, you just want to identify like what was being asked. So it was just the sample proportion. And if you want to add more context to this, it's the students who say that they will take another math class, which is pretty good. I mean, it's saying that 60% of the class of the students that take statistics will take another math class. Now, whenever we talk about the shape of the distribution of a sample proportion, there are two conditions that must be true. Now, one of those conditions, and I'll try to squeeze it in here, one of those conditions is that you have that n times p times 1 minus p is greater than or equal to 10. Another characteristic of which that we are going to say that p hat is normal is that the sample size must be less than or equal to 0.05 of the population. So we have that this will be denoted as big N. Now, this is more or less just the conditions of which that p hat is approximately normal. So we'll just say, for example, that these two characteristics is so that p hat is approximately normal. Now, one way of which that I kind of interpret this 5% of n is that in order to have a statistically significant study, you have to have that usually that that you're taking like large enough sample size in order to make like a type of inference off of the statistics for the parameters. So more or less, these are just the conditions that must be applied. If not, then we would say that the p hat is the sample proportion is not approximately normal. Now, one of the other things that I need to mention is that the mean for p hat is equal to the population proportion. The other thing of which that I can mention is the standard deviation. And that's equal to the square root of p times 1 minus p divided by n. Now try not to get too confused on like how do you get n. N is just the sample size again. And what we're saying is that the mean is actually the population proportion. So this describes the p hat distribution. Now one more formula. So a few of you have asked about z-scores, and z-scores is really just the deviation from the mean. So we know that the mean is p hat, so essentially we just need to take the p hat minus p divided by the standard deviation. Now we'll go ahead and just write that this is going to be the square root of p times 1 minus p divided by n. The only reason that I do this computation for the z-score is whenever I'm looking for my probability, which above we see that there's a probability example. And yeah, I guess I should have had this a little bit more spaced out. So we have that, we look at this example where we have a National Association of Realtors estimates that 23% of all homes purchased in 2004 were considered investment properties. If a sample of 800 homes sold in 2004 is obtained, what is the probability that between 175 and 200 homes are going to be used as investment property? Okay, so not too much to digest, but yeah, we just need to kind of like work this out in terms of like how do we approach this problem. So one of the first things that we should look at, okay, so let's just do this so that way you kind of know where we're going to work off of. The thing of which that we need to identify is that, see, okay, so we know that, for instance, that the mean for p hat is given by the 23%. So we have that that's going to be equal to p, but p is 0.23. Now, the next step is that we would find the standard deviation. So the standard deviation is equal to the square root of 0.23 multiplied by 1 minus 0.23. All of this is divided by the sample size, which in this case was 800. Okay, so once we do this approximation, this just gives us the standard deviation. So I found that when I calculated this that I get 0.0149. Okay, so this gives us the standard deviation. Now, there is a little bit of an issue when we talk about the conditions. So the issue is that, and I believe this question is from the textbook, the issue is that when you check the conditions is that when you look at n less than or equal to 0.05 times big N, there was no population size given. Okay, so there was no population size that was given. Now, in most cases, the population is given, which means that we would be able to justify that this distribution is approximately normal. But in this sense, we're going to have to just assume that it is approximately normal. But, most of the time you are given the big N. Now, if we look at the other condition is at least satisfied. So we have that N times P times 1 minus P is greater than or equal to, we say, 10. Okay, so for that, we just have that that's going to be 800 times 0.23 times, let's see, 77% should go right there because 1 minus P is 0.77, and that's greater than or equal to 10. That's because you end up with 141.68 greater than or equal to 10, which that's true. Okay, so at least like part of the conditions are at least satisfied. So we move on to the next step. The next step is that we were trying to figure out, okay, so note that, for example, that we were trying to figure out about the probability that 175 homes and we'll just say 200, yeah, that should be 200 homes. Now, interestingly enough, notice that the 175 homes and the 200 homes, they're not in the form that they need to be, in the sense that it's out of 800 homes. So if you want, you can actually divide everything by n. Okay, so we'll divide this by n. But normally I would have just wrote out right away. I would have just said the probability of 175 divided by 800 is less than p, and that's less than 200 over 800. Now, the next step would be that you would technically need to find the z-score. Let's go ahead and figure out, though, like what is 175 divided by 800. That way we can kind of clean it up a little bit, like in case like you're uncomfortable with the fractions. So 0.21875, let's just do 200. That should be easy though, divided by 800. 0.25, okay, so, and remember that the mean is 0.23, so we're pretty close. 0.21875. And that's less than 0.25. Now, here's the part that, it's really just a matter of preference in terms of finding the probability that your population proportion is between 22% and 25%. So, the part that, we can look up, for example, is the z-scores. So, like, for example, we have that there's going to be a lower, which means that you can take the p hat, I believe it's p hat, yeah, we already found p hat. P hat is this value right here, with 0.21875. So we just need to find that 0.21875 minus 0.23 is all divided by 0.0149. Now you're going to do the same computation for the high or the upper. Okay, so that's going to be 0.25 minus 0.23, and all of this is divided by 0.0149. So this part, to be honest, is not very necessary because we have that the calculator can figure out like how many deviations that the sample proportion is. So 0.25 minus 0.23, all this is divided by 0.0149. We hit enter and we get 1.34. Okay, so yeah, I'm trying to see like what's a good number of decimal places that we can take. Let's do 4. So 1.3423. Okay, so the upper is going to be 1.3423, and the lower, okay, so we still need to figure out the lower. The lower is given by, let's see, what did we say? 0.21875 minus 0.23, and then all of this is divided by the standard deviation of 0.0149. And when we hit enter, okay, so this is negative 0.7550. Okay, so that's not too bad. So, and if you're using the appendix for the z-scores, you just kind of have to get it as close as possible to the nearest one. So like if you have that your z-score doesn't fall in the list of scores, you can just kind of like take the average or just kind of eyeball it. Okay, so this is saying that our probability is between negative 0.7550, and that's less than z, and that's less than 1.3423. Okay, so we just need to figure out what that is. And no worries, I'm going to show you like how we could do this really quick. So normal CDF. Okay, so I have a few things still here. So negative 0.7550. And then 1.334. I think it was 23. Let's just go ahead and look. Yeah, that's right. Now here you need to change the mean to 0, and then you need to change the standard deviation to 1, and then just hit enter. Okay, so I'm getting, so this is 0.6851. So it might be a little bit off from what I got in my calculator initially, but it's only off by a few decimals, or it's only off by 3. It's accurate up to 2 decimal places, so it's off by like 0.003, which is it's not too bad. Okay, so this gives us, and it could be that there's some rounding error because I kind of rounded, not the p's, the p hats, but the z-scores is probably where it happened. So I'm getting 0.6851, and that's gonna be the answer. However, there's another way that we could have done this. So we could probably just say, okay, well, let's not even concern ourselves with z-scores. So we can go to normal CDF and just type in, well, we had 175 divided by 800. We have 200 divided by 800 also. Now the percentage, the mean was 0.23. The standard deviation was the standard deviation was 0.0149, and then we just click enter. Okay, so as you can kind of see, if you just scroll or just shift to the left, you'll see the whole list. Lower, upper, the mean is 0.23, and the standard deviation is 0.0149. So hypothetically, you just really need to calculate the standard deviation, and that's really it. And then, yeah, don't forget to divide the measurements by 800 because you want it in percentage. Okay, so this gave me 0.65, 0.68. Okay, so yeah, this gave me 0.6851, which means that I'm actually very close. I think I might have been thinking of another example, or maybe in my notes I used the wrong measurements. So it gave me 0.6851, which is about the same. So we'll just put that in using the probability of 175 divided by 800 less than p less than 200 over 800. I'm avoiding using the z-score. So we have normal CDF, and then we'll just use the 175 over 800. I'll just move this a little bit so that you can see it. Comma 200 divided by 800, comma 0.23, comma 0.0149. And then we just close that. And that's going to be approximately 0.6851, 51, which is the same thing if you use just the normal CDF. Note that again, that the way that you should be looking at it is that you have the low, and then you have the upper, then you have the mean, and then you have the standard deviation. But in our case, for this distribution, you had to make sure that you were putting the mean respectively with regard to the sample proportion, and then you have the standard deviation similarly with respect to the sample proportion. So again, the only thing that you really should be calculating is the standard deviation.